All right, so our first lesson here in chapter 7. Okay, you guys listen up. I'm on page 1. You have to kind of go past the definitions and the songs and all that kind of stuff in your packet. And so the first part of this is peer review. Um, writing the equation of the line from this data. We are actually not going to take the time to graph it just because I'm going to save us some time here. I just want to say that I want to make sure that you label your graphs in the event that you have to do that. So let's kind of talk through this problem and start doing the review things, then we'll learn a couple of new items to go with it. So this following data gives the data for ice cream sales and the temperature in degrees Celsius. So which one of those variables do you think would be the explanatory variable between temp and ice cream sales? Which one? Okay, good. So our temperature is the explanatory variable. And then what is the response to that particular temperature? Our ice cream sales, and I'll abbreviate it with just sales. Now, I'm not going to have you plot all of these points on this graph, but I want to make sure that upon you doing that you make sure that you label it, in temperatures in degrees Celsius or however that is. Okay? So just make sure, I'm going to let you omit this graph. I'm going to let you omit that on your homework as well, just because, I don't know if I'm going out on a limb here, but I'm kind of thinking that you can plot points onto a graph. So, okay. All right. So we're moving forward. Now, I want to have you write the equation of this line that will best fit this data. So what happens is we end up having this data on our chart. It may look something like this. Okay, because real data isn't all nice and pretty. Okay, so the data all might be something like that. And so how would I find the line of best fits for that? Okay, we're going to use our calculator. And I'm going to have you all do this because there is something later that you need to make sure you have your calculator for. So if you don't have one, make sure you've got that out and you're working on that. Where are you going to go to do that in your calculator? Stat Edit. So go to Stat Edit, put your X values into list 1, put your Y values into list 2. Go ahead and put those in there. So once you have your stuff in there, then you're going to go ahead and do your stat over to calc, and we want to get the linear regression, which you have done in the past in your classes as number 4. Okay, stat calc number 4, enter, and then there you have it. Now, we are going to be needing the R value and the R squared value. That's the two new things we're going to be learning about today. So raise your hand if your calculator does not give you that R and R squared. Okay, good. So that means that whether you get it or not, whether it comes on your calculator or not, I do need you to pay attention to how to get it to show up. I'm going to show you 2 ways to get the R and the R squared to show up, because sometimes depending on how, if you clear your calculator or various things, it might not show up and you need to know how. 2 ways. Way number 1 to get the R and the R squared to show up is if you have a newer calculator that has an updated operating system, then you go to mode, and on this mode it'll give you the one of the options down here is to look at the stat diagnostics. Okay, so if you take a look down here at the bottom, you've got stat diagnostics on or off. That is what will give you the R and the R squared. Okay. Now, on the other stuff that we were doing, when we would do inverse norm and norm CDF, and some of you guys would have a menu that shows up and you have to keep like hitting enter and going through all of that, I personally find that annoying and I don't like it. So you can change that. That is found with your stat wizard. And you can turn that off if you don't want to have to always go through the menu when you do the norm CDF and inverse norm and such. So if you go to mode and you have this option, that's easiest for you, turning the diagnostics on. Okay, now the rest of us, though, who don't have that as an option, We'll have to go and look in the catalog. Look in the catalog, and that is found. You can always find everything that the calculator has in the catalog above the number 0. So you will press second 0, and that'll give you an alphabetical list of everything in the calculator, starting with absolute value. Okay? The issue is you have to get down to the letter D. And the letter D is actually quite a bit of pushing the arrow down. It'll take you a while, so we're going to jump ahead to the letter you want to go to. And if you take a look at all of the letters above the buttons, the letter D is above X to the -1 button. And that'll make it jump straight to that portion of the alphabet. So I went to the letter D, and now I'm going to go down and find diagnostics on. By the way, there's your detect your asymptote and stuff. So if you're in calculus or pre-cal, maybe even when you'll get to asymptotes, I don't know if your teacher shows you that or not, but that's a feature your calculator can do. So I turned the diagnostics on, and once I hit enter and it says done. Now the diagnostics are on. I can do the stat, calculate it again, stat calc number 4, and now the R and the R squared will show up. All right, anybody stuck without the R and R squared now? Okay. All right. Yes? Okay, so now that we have our equation of our line, we're going to write that down in context. So our Y variable is sales. So go ahead and write down your equation of the line, putting in the words for the variables. Okay, so that's what I want you to do with it in context. Okay? Now, so all of that so far is just everything straight from Algebra 1, such. Now, here's something that is particular to how specific we get in statistics, okay? We cannot just say that the sales equal 30.09 times the temp, because what that says is that every piece of data is falling on this line. It is exactly equal to what is on this particular line. But do we have things not on that line? Yes. That is a prediction line. That's giving us an estimate of what we think that where our data is going to fall. So therefore, this answer that you have written on number 4 is wrong unless you have a prediction hat, kind of like a sorting hat. You have a prediction hat on sales, because this is saying that the predicted sales is 30.09 times the temp minus 159.41. Predicted sales. I will mark it wrong. AP will mark it wrong if you do not have that prediction hat. All right. Now let's interpret the slope. So tell me in context, what does that $30.09 mean? Good. $30.09 increase for every degree that you go up. Okay, good. And so I have a song to help with that, because it'll also help us make sure we get that predicted going in there. Okay? So here's our song for Interpret the Slope. I don't have the video made yet, so we're just going to be a cappella today. So it's Adam's Family. So the key that we have going on is that for every one increase in the X, the predicted Y will do what it is that you're talking about. The predicted Y. So for every one increase in the X value, and I have it in quotes because we would want to make sure we did context, the predicted Y value, and in our case it'll go up $30.09. So here we go. Interpret the slope. 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 For every one increase in the X, the predicted Y, it does this. Interpret the slope. Interpret the slope. Interpret the slope, interpret the slope, interpret the slope. Okay, one more time. Here we go. For every 1 increase in the x, the predicted y, it does this. Interpret the slope, interpret the slope, interpret the slope, interpret the slope, interpret the slope. All right. So let's see if we can use that and interpret our slope. So how are we going to start that? For every one increase. And so I'm going to go ahead and put for every 1 degree Celsius increase, because, you know, the song helps you, but you got to put that context in there. So for every 1 degree Celsius increase in the what? In the temp, or in the x. For every 1 increase in the x, what's x? Temp. Okay, so for every 1 degree Celsius temperature, or increase in the temp, the what? No. The predicted y, the predicted sales go up $30.09. Okay? For every 1 degree increase in the temp, the predicted sales goes up $30.09. All right, now we're going to interpret the y-intercept. So our y-intercept, of course, being negative 159.47. Now I want you to take a look at this graph up here. This can happen. This can happen because all your data is located out here where we had some higher level temps. And out here where we have higher level temps, maybe that's positive, you know, a linear shape. Okay? But it could take on a different shape once you get farther out. This shows it continuing down in a straight line and making that amount, that sales, negative 159.47. So where does the y-intercept occur? Where is the y-intercept occurring? What is our temperature at that point? 0. Good. When the x is 0, that's when we have our y-intercept. So when the temperature is 0, our predicted sales are that negative 159.47. Frequently, the y-intercepts do not make sense because they're this concept we'll learn later called extrapolation. They're far away from the data you used to make your equation. The y-intercept was far away from the data you used, and the pattern could change by that point. So okay, so the y-intercept song goes to the wrecking ball, the chorus to the wrecking ball. Okay, so here we go. It's the interpret the y-intercept. It happens when the x is 0. The predicted y is this, and it often does not make sense. Okay, see? So it's happening when x is 0. Okay, so we know that. Happening when x is 0. The predicted y is that amount. And because of extrapolation, which we'll talk about later, it often does not make sense. So y'all ready to sing that with me? I don't know if it's very singable, but here we go. Interpret the y-intercept. It happens when the x is 0. The predicted y is this. And it often does not make sense. Okay. So let's go to our work here and fill in that information. All right, here we go. Let's write this out. So what are we going to say then for our interpret the y-intercept? It happens when the x is 0. So what's 0? Good. When the temperature is 0 degrees Celsius, the what? Good. The predicted sales, is it R or is? Are negative $159.47. Okay? All right. is really relatively, old stuff, review. Okay, I just kind of put a little spin on a few of them and making sure that we're predicted and making sure we have some way that we can say those statements. So the next thing is we're going to learn two new things. One is a correlation coefficient represented by the letter R, and one of them is coefficient of determination represented by the letter R squared. And so I want you to turn over to page 4 in your packet, and that's where we're going to start with the notes part 2, and that is going to be our correlation coefficient. So here we go. So the correlation coefficient is represented by a lowercase letter r. And we already went through that in our calculator to show that to have that show up. It measures the strength and the direction of a linear relationship. So we're talking about linearity, a linear relationship between two variables. It measures, in a sense, how clustered the data is around the line. Okay, it's represented by lowercase letter r, and it is a number. The value of the r values go from -1 up to +1. Okay, so in a sense, you can see that we would have the positive values if we're having positive slopes, and we would have the negative values if we were having the negative slopes. But when you are at 0, that is saying no linear correlation. So I have some pictures as guidelines here. Look at this first one on the left. What does this look like much of a linear correlation? No, its R value is 0. As opposed to the opposite of that, over here, all of our dots fall exactly on a straight line. So that is a perfect linear correlation, and hence that correlation coefficient is 1. Now, if you take a look between the two remaining pictures that are left, and you imagine, putting your line of best fit in there, one of them is an R value of 0.9 and one of them is an R value of 0.6. Do those two graphs look different from each other? And if so, how? Okay, good. So the 0.6 is more spread out around the line. The 0.9 is more closely clustered around the line. What concept have I talked about in the past where I talk about it being more closely clustered around the certain area? Standard deviation, absolutely. You will never have to compute R by hand. It is based off not only the standard deviation in the X direction, but the standard deviation in the Y direction. So it's like two-dimensional standard deviation stuff going on. Okay, that's in a sense. There's some more stuff involved there, but that is what's partly happening. All right. I wanted to point out that it is a measure of linearity. So if you have something that's, say, quadratic shaped, it is not appropriate to describe it with a strength of R. Okay. Furthermore, I have seen questions where if you have, say, something like a quadratic relationship, I have seen AP questions that ask you if a R is 0, does that mean that there is no relationship? The point is, if R is 0, there is no linear relationship. There could be a beautiful quadratic relationship, okay, but there may be no linear relationship. So that's kind of a little sneaky word that has to be in there. All right, now let's talk about the phrase that you will use to talk about to interpret the correlation coefficient. You will talk about the strength and the direction. So you'll say there is a strong or there's a weak, and the direction is that there is a positive or a negative. You want to include that it is a linear relationship or a linear correlation between your explanatory variable, so between your x and your y. All right? So, and you would put those in context. You wouldn't just say x and y, you would use the words that describe it. Okay? So, I have got something for that. Let's see if I can find it. It goes to blue suede shoes. Anybody know somebody who can rap? Because I'm going to have to make this Ice Baby one, and my voice is not a rapping kind. You got that one? You're going to help me with that later? Okay. All right, so correlation coefficient, though. let's take a look at the words that go with this. There is a strong or there is a weak, positive or negative, linear correlation between X and Y. Linear between X and Y. All right, so it's the blue suede shoes, and I don't have the video or the music on hand for this. I'll get it, but don't have it right now, so here we go. I'll sing it, and then you guys can come in because you kind of hear how it goes. There is a strong, there is a weak, positive or negative, linear correlation between X and Y. Linear between X and Y. Okay, you guys come on in this time. There is a strong, there is a weak, positive or negative, linear correlation between X and Y. Linear between X and Y. Good. One more time. There is a strong, there is a weak, positive or negative, linear correlation between X and Y. Linear between X and Y. And then I got to get that it's got the letter R that goes on, so I'm going to put the little jazz ending, the R, at the end of it. Okay, so that is the correlation. Let's now interpret this situation. So here we go. The following graph is a representation of data about the price of a pumpkin and its diameter in inches. Do you think that the diameter has a bearing on the price of a pumpkin? Do you think the diameter? Yeah, probably. Okay, because you know we got Halloween coming up here soon. So this is an R value of 0.7. Well, let me kind of give you a guideline of what's strong and what's weak and all that kind of stuff. So this is a general guideline. It's not set in stone. Some particular disciplines are all focused in the 0.9s, so they'll, want to be accurate to the hundredths place or something. But we're going to say that something that goes from 0.0 to 0.3 is weak, practically no linear relationship. In the middle is the 0.4s to the 0.6. So the 0.4s to the 0.6s are pretty moderate. 0.7s to 0.9s are strong, and then of course 1 is a perfect linear relationship. So these also are mirrored in the negative direction. So an R value of 0.7 would be what kind of strength? Yeah, that's our strong. So we're going to start off. There is a strong. It's not weak, and then what else comes next? Positive or negative, and so in this case it's positive. And then what's next? Positive or negative? Linear. Okay, so linear relationship or correlation, either way, between what? X and Y. And you have to write the context down, of course. Good. So the price of pumpkin, and the X and the Y can be switched here, and its diameter. Okay? Probably. What does it say? Oh, in inches. Yeah. All right. Very good. Now, you know how when you go to a superstore, it kind of makes and you buy like in bulk, it makes the price per ounce maybe less? Well, this idea goes along with that. Example 2 is about the size of a farm, the pumpkin farm, and the price per pound that they charge for their pumpkins. So it is negative related because as the size of the farm gets bigger, it's like a big farm, they charge their retail clients or their wholesale clients less. Okay? So what would we say about this? How would we describe this correlation? Good. There is a weak, negative, and what's next after that? There is a strong, there is a weak. Positive or negative? Linear. Good. Correlation between X and Y. So correlation between size of farm and price per pound. Okay, very good. All right, so that is correlation coefficient. let's go to page 1 and I want you to write the correlation coefficient for the temperature and amount of ice cream sales. So think back to our original problem, temperature and ice cream sales. So go down here, look on your calculator to find R. Look on your calculator to find the R value. Okay, there's a strong positive linear correlation between temperature and sales. Okay, next is R squared, which literally is the R value squared. Okay, so in this case, we'll go ahead and write that down. In this case, R is 0.96. Here, if you have 96% of 96, you get the number 92, so 0.9, so R squared equals 0.92. And now let's go learn what that means. Okay? So if we go over in our thing to page, I think 6 or so. Yep, page 6. Okay. This is a little bit more abstract of a concept, so I kind of want to give you an idea of what's happening before we get into the definitions. Otherwise, I'm just rambling off words in the definition that don't really make sense. So, what R squared has to do with is it's kind of talking about what is explaining the changes in in this case, sales. So it's saying something to this effect. Not exactly, not completely, but this is kind of the general idea. The reason that the sales are all different prices, the reason that there is variability, fluctuation in the sales of the ice cream is because there is fluctuation in the temperatures outside. So it has to do with the variability of those things, not just one pinpoint item. So the reason that fluctuation is happening in the sales is because there is fluctuation in the temperature. Okay? And what an R squared tells you is the percent that of reasoning that you can attribute to it. For example, we just said our R squared was 0.92. So 92% of the reason that the sales fluctuate, 92% of the reason that the sales fluctuate is because the temperature is fluctuating. 92% of the reason that the sales are fluctuating is because the temperature is fluctuating. That means 8% is attributed to other things. Why else could the sales be fluctuating? Amount of people that come. The what? There's a sale. Okay, you put it on sale. Bluebell is in season and not having a listeriosis sale or scare, whatever. Okay, yes. Time of day. Okay. Although that's cyclical and I don't know. So anyway, so that's kind of in general what's happening. So let's now go through this with that concept in mind. So R squared is based on the fluctuation of that y variable that can be predicted by the changes in the x variable. Because it is R squared, it has to be a positive number. So you are literally taking the R values, you are squaring them. Therefore, R squared numbers go from 0 to 1. And when we get this number, we will represent it as a percent, kind of a percent of the reason that something's happening. So I have a song for that, So let me kind of teach you how you say this with a song, and then we'll sing it. It's to Frosty the Snowman, so it's kind of a fun one to sing. So the percent of variation in the Y. For example, we were saying 92% of the fluctuation in sales. Okay, so the percent of fluctuation or variation that is happening in the Y. So coefficient of determination, the percent of variation that is found in the Y, and now can be explained by those changes in the X. So in our situation, that the 92% of the fluctuation in the sales can be explained by those changes in the temperature. They can be explained by the changes in the temperature. But I've also seen textbooks say that they can be explained by the equation of the line. So I wrote in here, or it can be explained by the model itself, the linear model that goes with it. Okay, so that's the two ways that they go through that. So let me sing this one. Well, I don't know, you might be able to sing it straight off with me. So here we go. Coefficient of determination, the percent of variation that is found in the Y. Coefficient of determination, the percent of variation that is found in the Y. It can be explained by the changes in the X, or it can be explained by the model itself. Oh, coefficient of determination, the percent of variation that is found in the Y. All right, so let's sing it one more time, and then we'll go put them in our packet. Here we go. You ready? Everybody sing now. Coefficient of determination, the percent of variation that is found in the Y. Coefficient of determination, the percent of variation that is found in the Y. It can be explained by the changes in the X, or it can be explained by the model itself. Oh, coefficient of determination, the percent of variation that is found in the Y. Okay, so let's put that in here. On this packet, let's practice this with the problems we just had on the previous page. The first one we had was the price of the pumpkin and its diameter, and that one was an R value of 0.7. So if that's the case, what would the R squared value be? 0.49, because 0.7 squared is 0.49. So I'm going to go ahead and straight up tell you this one, and then you'll start getting the hang of it. So this means that about 49% of the fluctuation or the variation in the cost of the pumpkins, okay, about 49% of that variation in the Y, it can be explained by the changes in the X. So can be explained by the changes in the diameter. So 49% of the reason that the pumpkins all cost different amounts is because of the varying diameters. Why else? That means 51% of those changes are attributed to something else. What else could be attributing to the different prices of pumpkins? If they have bruises, yeah, their quality, the type of pumpkin they are, the coloring, where you purchase them. Okay, Walmart versus Central Market. I mean, boom, right there. Okay, so we know 49% is happening because of the changes in the diameter, that size. All right, example 2 was about the size of the farm and the price per pound. price per pound, and that R value was negative 0.3. So therefore, what's the R squared value? 0.09. Is that very much? I mean, this was a weak correlation, remember? So I'm going to say only about 9% of the variation in Y. What's that Y value? Nope. Y is the price per pound. So only 9% of the reason that you have different prices per pound only 9% of the variation of the price per pound is explained, can be attributed to, is explained by the different farm sizes. So that means there's a whole heck of a lot more that goes into why you have different prices per pound. All right, so that's all on that. Let's now go back to your very first page and have you take your R squared of 0.92 with sales and put the explanation that goes with this. Okay. So there's your answer for that. About 92% of the variation in sales can be explained by those changes in the temperature. 8% is happening because of something else. 8% of the reason that there's other things is happening because of something else. Now, your homework is to do 2 of these pages of your own. And I will let you omit doing the graphs on them. So you are just going to put data in and answer all the same questions that we answered today, and you are going to practice that twice. Okay, pages 2 and 3 is your assignment tonight.